Okay, so we are trying to understand the mapping properties of the modular function lambda, which is invariant under the action of the congruence mod 2 subgroup of PSL2C. So let me quickly recall what we are trying to prove. So we have this function lambda of tau, which is given by E3 tau minus E2 of tau by E1 of tau minus E2 of tau. Lambda is defined on the upper half plane and taking values in the complex plane, and in fact it does not assume the values 0 and 1, okay, and is analytic, never is equal to 0 or 1, okay, and the claim was the following, that if we take the following region in the tau plane, this is the tau plane, we take this line segment which is given by real part of tau is equal to 1. So this is the point 1, this is the origin, and then we take this point given by half and consider the semicircle centered at the point half and radius half. We take this region omega, this region. The boundary of omega consists of this positive part of the imaginary axis and part of this semicircular arc, and then this positive part of this line parallel to the imaginary axis, okay. And then the claim was that so the theorem we are trying to prove is that is lambda maps omega holomorphically isomorphic, onto the upper half plane, okay, in a one-to-one manner, okay, which is the same as saying that lambda from omega to the upper half plane is a holomorphic isomorphism, okay, and further extends to the boundary of omega, okay, continuously, so that you see infinity, the point at infinity, the origin and 1 are mapped onto 0, 1, infinity respectively, okay. So this is the theorem we are trying to prove, that lambda maps, see the lambda is defined on the upper half plane and it takes complex values. What we want to say is that if you consider only this region, then lambda maps the interior of this region, by omega I mean the interior of this region, it maps the interior of this region onto the upper half plane in a one-to-one manner, and you know when a holomorphic map is one-to-one, you know it is a holomorphic isomorphism onto the image, which is an open set, and further you can extend lambda to the boundary of omega, so that this extension is continuous, and the point at infinity 0 and 1 are mapped onto 0, 1 and infinity in the target plane, okay, in the lambda plane, alright. So this is the theorem we are trying to prove, and as it happened the proof of this theorem is extending to a few lectures, because one has to do extensive computations, okay. So let me recall what we did, what we have done so far, okay. So what we have done so far is the following. What we have proved so far is that the first thing is lambda is real on the boundary of omega except the points 0 and 1, okay. So you see what I want you to understand is lambda is already defined an analytic on the upper half plane, so the really difficult points are the really difficult points in the boundary are the points 0 and 1, okay. So the point is that you will have to show that lambda approaches a genuine limit as you approach this point from within omega, and you have to similarly show that lambda approaches a genuine limit as you approach this point from within omega. That is what you have to show, alright, and you must show that this limit is independent of the way in which you approach this point, so long as you are inside omega. Once you do that, then you can extend lambda to 0 and 1, okay. So I will have to essentially show that if tau is inside omega and tau and also on the boundary of omega, and suppose tau tends to 0, I will have to show that lambda of tau goes to 1, and if tau tends to 1, then I will have to show that lambda of tau goes to infinity, okay. So but on the other hand, so you see if you do not worry about these 2 points, on the rest of the boundary, okay, lambda is certainly real, okay. If you remember, we proved that whenever tau is purely imaginary, we proved lambda of tau is real, okay, and then you see the and then you see this line, a real part of tau equal to 0, which is the imaginary axis, that is mapped to this line by the transformation tau going to tau plus 1, and you know lambda of tau plus 1 is related by a functional equation in terms of lambda of tau, and therefore the fact that lambda of tau is real on this line will tell you that lambda of tau is also real on this line, okay, on this half line, as you may think of it, and then this half line is mapped onto this semicircle by the transformation tau going to -1 by tau plus 1, that is 1 minus 1 by tau, okay, and therefore and again lambda of 1 minus 1 by tau is can be expressed in terms of lambda of tau because of a you know functional equation or a recursive formula, and therefore the fact that lambda is real on this line will also tell you that lambda is real on this line. So we have therefore proved that lambda takes real values on this boundary. The only problems to be settled are at what happens at 0 and 1. So the second thing that we proved is we proved that as imaginary part of tau goes to plus infinity, then we proved that lambda of tau dies down to 0 in a way that is uniform with respect to real part of tau, okay. So let me write that down. Lambda of tau tends to 0 uniformly in real part of tau if the imaginary part of tau goes to infinity, okay. So this is what we have so far established. Alright. Now what I am going to prove is, now I am going to use these functional equations and tell you why lambda of tau as tau tends to 0 goes to 1, and why lambda of tau as tau tends to 1 goes to infinity. Okay. So well, that is very easy to see. So let me explain that. Put tau is equal to I times imaginary part of tau. Okay. So you see I am taking tau on the imaginary axis, so tau is purely imaginary, alright, and of course imaginary part of tau is of course greater than 0. I am in the upper half plane. Okay. And then look at, let me use a functional equation. So you know I want to calculate lambda of 0, therefore the obvious thing that I will do is I will try to calculate lambda of 1 by I times minus 1 by I times imaginary part of tau, and let imaginary part of tau go to infinity. Okay, that is the most obvious thing I will do. And then I have a formula. So if you recall from these functional equations, one of them is lambda of minus 1 by tau is 1 minus lambda of tau. So you see lambda of minus 1 by tau is 1 minus lambda of tau. Okay. So we have this functional equation, and what you do is in this functional equation I will put tau equal to imaginary part of tau. So I will get lambda of if I substitute this here, I will end up with minus 1 by I is of course I, so I will get I by imaginary part of tau is equal to 1 minus lambda times I imaginary part of tau. Okay. Let imaginary part of tau tend to 0 plus. Okay. Then so what you are doing is so you are letting tau to go to you are letting tau to approach 0 along the imaginary axis, alright. So then you see lambda, so then what will happen is you will get lambda of so I by imaginary part of tau will go to infinity. Okay. And you see but you see lambda of the lambda of this will be 0, okay, as I let imaginary part of tau to go to 0 plus. Therefore I will get lambda of tau to be equal to 1, alright. So let me write that down clearly. So you see limit imaginary part of tau tending to 0 plus of lambda of I by imaginary part of tau. What is this? This quantity is I should say limit imaginary part of I by imaginary part of tau going to plus infinity of lambda of I by imaginary part of tau. Okay. But this is, as we have seen, this is 0. Okay. So this is equal to 0, alright, uniformly in the real part of tau, of course, but in this case real part of tau is 0 because you are on the imaginary axis. On the other hand, if you take on this side limit as imaginary part of tau tends to 0 plus of 1 minus lambda times I imaginary part of tau, so you see this has to be 0, alright. So what it tells you is that, so this tells you that lambda of tau tends to 1 as if tau is purely imaginary and the imaginary part of tau tends to 0 plus. Okay. So the moral of the story is that, you know, if I, let me draw that diagram again here. So you see so here is my region. So as I approach along this line, okay, lambda approaches 1, that is what I have proved. Okay. As I come along this line, lambda approaches 1, and notice that notice that if you approach 0 by any sequence of points inside omega, this sequence of points whether it is a discrete sequence or even if you approach continuously, in any case because it is being caught between a portion of the arc of this semicircle and this and the imaginary axis, it has to come infinitesimally close to the imaginary axis, and in the upper half plane lambda is of course analytic, so it is continuous. Therefore what this will tell you is that so long as you are within omega or on the boundary of omega, if you approach if you let tau to approach 0, then lambda will take the value 1. So this tells you that at 0 you get there is a well defined limit for lambda and that is 1. Okay, so hence limit tau tends to 0, tau in omega, so I should let me put tau in omega closure. Okay, so I will include the boundary also, lambda tau is actually 1. Okay, so that settles the fact that lambda maps 0 to 1. Alright, then again, so the similar trick will tell you that lambda will send 1 to infinity. Okay, so so let us prove that for that you make use of another you make use of another functional equation. So what I do is I consider so now what I will do is that I will consider so you see here I consider tau on this line. Now let me consider tau on this line. Alright, so what you do is put tau equal to put tau is equal to 1 plus I times imaginary part of tau. Okay, that is constrain tau to be in the upper half plane with real part of tau equal to 1. Alright, put this, and I am trying to show that you see letting tau to tend to 1 along this line is the same as trying to let imaginary part of tau to tend to 0, and I am trying to calculate what is lambda of tau. So you see you will get lambda of tau will be just lambda of 1 plus I times imaginary part of tau. Okay, but then there is a recursion formula which says that there is a functional formula which says that lambda tau plus 1 is lambda tau by lambda tau minus 1. Okay, so this will be lambda of I times imaginary part of tau by lambda of I times imaginary part of tau minus 1. This is because of the functional equation that lambda satisfies. Lambda of 1 plus tau is lambda tau by lambda tau minus 1. I am using that. Okay, and now you see, therefore you see if I take limit as the imaginary part of tau tends to 0 plus, okay, then this is the same as taking limit as this limit is the same as taking the limit as tau tends to 1. Okay, these two are one and the same, and of course tau is approaching 1 from above, from the upper half plane. Okay, and therefore limit tau tends to 1 of lambda of tau, okay, of course with tau with of course real part of tau equal to 1, okay, is for this side I can take the limit as imaginary part of tau tends to 0 plus, but I have just now proved that you see if imaginary part of tau tends to 0 plus, I times imaginary part of tau is here and lambda approaches 1. Alright, therefore the numerator approaches 1, the denominator approaches 0, therefore this tends to infinity. Okay, so this will be limit imaginary part of tau tending to 0 plus of this quantity and that will be infinity. Okay, that will be the point at infinity. Therefore, this argument tells you that as I approach 1 along this line, lambda approaches the value infinity. Okay, the lambda approaches the value infinity, and now it is clear again because of the fact that lambda is analytic in the upper half plane, that if I approach along any path which is inside omega or on the boundary of omega, lambda as tau tends to 1, lambda of tau will certainly tend to infinity. Okay, so hence so I will have limit tau tends to 1, tau in omega bar, lambda of tau is infinity. Okay, so what we have succeeded in proving is that certainly you can extend lambda to the you can extend lambda to the boundary. Okay, with lambda at 0 being defined to be equal to 1 and with lambda of 1 defined to be equal to the point at infinity. Alright, you can extend lambda, right, and you must always remember that since we are since omega is an unbounded region, okay, when we take the boundary of omega, the point at infinity also has to be taken into account. Okay, and we have already taken that into account when we proved that literally lambda of infinity is 0, is defined as 0. Okay, this tells you that you can define lambda of the point at infinity as 0. Alright, so so essentially though we are drawing diagrams on the finite part of the plane, both in the tau plane and in the image plane, you must always remember the point at infinity. Alright, so well, so far so good. So here let me draw the diagram once more. So you see you have so here is omega. Okay. So let me look at let me preliminarily draw this diagram. Okay, let me take omega, so let me write this as lambda equal to lambda of tau. Okay, so what happens is that I get so you see this is the tau plane, and then I get the lambda plane, alright, and I know that here lambda approaches 0. Okay, as I go higher and higher above, then I am making imaginary part of tau sufficiently large, then you know lambda approaches 0. So the point at infinity is being mapped to this point at 0. Okay, then so this is lambda of 0, this is lambda of infinity. Alright, then if I come down along this line from the point at infinity, if I come down along this line, okay, then as tau approaches 0, lambda approaches the value 1. Okay, so what happens is that this thing by continuity, you know, and you know lambda is real on this. Okay, so what you will trace is that you will trace a portion of this of the real axis, and you will reach the point 1, which is actually lambda of 0. Okay, and well, and from here if I continue moving along this circle, so you see let me draw an orientation. So you see now if I continue along the semicircular arc and come to this point, which is 1, lambda of 1 goes to infinity. So what happens is that so you know as I trace this, it's going all the way, it's going to go all the way to infinity. It's going all the way to the point at infinity. Okay, so So the information we have been able to gather is only this much, okay. We will have to do some computations to really trace out the image of this region, but what we will do is that we will try to trace out we will try to trace out the image of this closed path, okay, by taking this line segment and assuming that this y intercept is quite large, okay. You assume imaginary part of tau is large enough, alright, and then one would like to draw a picture of how the image of this restricted region, okay, this closed bounded region, how does it look in the lambda plane, that is what we would like to understand, alright. So what I want you to understand is that this is the and actually trying to understand that will give you an idea of it will literally prove this theorem, okay. We will prove the theorem in trying to understand this mapping, okay. So let me first explain a few things. So what I will do is so for that the first thing that I need is I need to make an estimation, alright. So this estimation has got to do with again with trying to expand lambda in terms of a Fourier expansion, okay. Namely you will have to involve sines and cosines of multiples of tau, okay, half integral multiples of tau. So let me recall, so we will so let me do the following thing, let me give some names to these points. I will call the origin as O, let me call this as A, okay, then let me call this as B, okay, and I will call this as C, okay, alright. And the question is we want and let me put lambda omega above, okay, let me put omega above, and what we want to know is we want to trace the image of this curve OABC in the lambda plane. See, this is what we want to do. In fact, and why do we want to do that? Because if you do that, it will explain to you why lambda is a one-to-one holomorphic mapping, which takes every value in the upper half plane, alright. So we want to do this. For this we will need the following computation, limit as imaginary part of tau tends to plus infinity, okay, of lambda of tau is lambda tau by e power I pi tau, this is equal to 16, okay. We will need this computation, alright. So see the point is the following, the point is that you know that as imaginary part of tau tends to plus infinity, you know lambda of tau tends to you know lambda of tau tends to 0, right. As imaginary part of tau tends to plus infinity, one knows that lambda of tau tends to 0. As imaginary part of tau tends to plus infinity, one also knows that e power I pi tau that will also tend to well, e power I pi tau is going to be what, it will want that also go to 0. If the imaginary part of tau goes to infinity, it will go to 0, right. So the point is, because e power I pi tau will be, if you write tau as x plus iy, alright, this will be e power I pi into x plus iy, so it will be e power I pi x, which will be modulus 1, into e power I pi into iy will be e power minus pi y, and if you let y to tend to infinity, e power minus pi y is going to go to 0. So both these fellows are going to 0. The point is this, what this formula says is that lambda goes to 0, you know, in such, you see it goes to 0 in this way, in this rather funny way, okay, and you have this number 16 turning up, okay, and I need this to get hold of that, to trace the image of this there. I need this estimate, okay, I need this limit. So let's have some fun trying to prove this, okay. So recall, so for the proof of this, so we'll have to prove this. So let me recall something. You may recall that lambda of tau is actually E3 of tau minus E2 of tau by E1 of tau minus E2 of tau, and this turned out to be the following expression. You know, we arrived at this in an earlier lecture by looking at the infinite expansion for pi by sin pi z the whole square, alright. So this is going to be so it is going to be summation n equal to minus infinity to infinity pi squared over cos squared pi n minus half tau minus pi squared over sin squared pi n minus half tau, okay. This is what E3 minus E2 turned out to be, and E1 minus E2 turned out to be sigma n equal to minus infinity to infinity pi squared by cos squared pi n tau minus pi squared by sin squared pi n minus half tau, okay. So in fact this is how we proved that as imaginary part of tau goes to plus infinity, you see the numerator goes to 0 and the denominator will go to pi squared, because only the n equal to 0 term will survive, alright, because all the moduli of all the denominators, they will all go to infinity so long as an n is involved, okay. So the numerator goes to 0, the denominator goes to pi squared, so this whole expression which is lambda of tau therefore goes to 0, and this convergence was uniform in the real part of tau because these series are all uniformly convergent, okay. So now you see, now let us compute, let's compute the following thing. I want to compute what happens to lambda t by e power I pi t as imaginary part of tau goes to plus infinity, but you see the as imaginary part of tau goes to plus infinity, the you see I am just comparing the orders to which these two vanish at infinity, and I am saying that the ratio, though each goes to each vanishes at infinity, but the ratio is finite, and that's what this says, okay. So but you see the vanishing of lambda tau is essentially due to the vanishing of the numerator, okay. So what I will do is, let me compute the limit as imaginary part of tau tends to infinity of the numerator divided by e power I pi tau, okay, because anyway we know that the limit as the imaginary part of tau tends to plus infinity of the denominator is pi squared, okay, because that is a contribution you will get from the term n equal to 0 corresponding to this term, which is the only term that will not involve n when I put n equal to 0, right. So yeah, so limit, so let us calculate E3 of tau minus E2 of tau over e power I pi tau. Let me calculate this. So this is going to be, well, I am going to get sigma n equal to minus infinity to infinity. Maybe I can maybe it will help to remove a pi squared outside, alright, and then you know I use the usual formula that cos theta is you know e power I theta plus e power minus I theta by 2, and sin theta is e power I theta minus e power minus I theta by 2i. So I use that to rewrite these in terms of e power I pi n minus half tau and e power I pi so the numerator in terms of e power I pi n minus half tau. So what I will get is I will get well I will get so I will have an e power there, so there is an e power I pi tau outside, okay, there is an e power I pi tau outside, right, and I pull the pi squared outside. I get, so the first term I get is 1 by you know e power I pi n minus half tau plus e power minus I pi n minus half tau the whole squared, and I will get a 4 in the numerator, okay, plus so then I will get here I will get e power I pi n minus half tau minus e power minus I pi n minus half tau and I will get a squared, and you see there is a 2i squared in the denominator will go to the numerator, that will become a minus 4, and because there is already a minus this will become a plus 4, okay. So this is what I get. Now what I am going to do is I am going to write this e power I pi tau as e power I pi by 2 tau, that is e power I pi tau by 2 the whole square, and push it inside I am going to push it inside the squares in the denominators. So that will lead to the following, so e3 tau minus e2 of tau divided by e power I pi tau will be, I am going to push this e power I pi tau inside, and I am going to, when I push it inside it shows up as e power I pi tau by 2, alright, and so then what I will get is I will get pi squared sigma n equal to minus infinity to infinity. I will get 4 by, so in fact I think I can get the 4 out as well, alright, and I will get 1 by well so you see if I add an e power I pi tau by 2, okay, then so what I will get is I will get e power I pi so I will get an e power I pi tau by, so this half tau is going to go away, so I am going to just get e power I pi n tau, alright, here because I have an e power I pi minus half tau, that is going to cancel with this e power I pi half tau, alright, and here I am going to get minus e power minus I pi so you see it is minus of minus half tau, so it is a plus half tau and another plus half tau, so I am going to end up with n minus 1 times tau, this is what I get, right, and there is a plus here, this is what I get, alright, and the second term will be same kind of term 1 by, I will get here again I will lose this half tau, so I will get e power I pi n tau plus, and here I will, this minus half will become minus 1, so I will get minus e power minus I pi n minus 1 times tau, the whole square. This is what I am going to get, okay, if I push this 1 by e power I pi tau inside the square, right, and you see now you see that if I let the imaginary part of tau to go to infinity, the only terms that will survive are going to be the terms in which no argument appears, okay, in the power. So you see the only, if I, the only terms that will survive will be terms that correspond to n equal to 0 and n equal to 1, okay. If I take a value of n different from 0 and 1, then all those terms are going to go to 0, okay. So you see if we let imaginary part of tau to tend to plus infinity, okay, the only terms that survive are those for n equal to 0 and n equal to 1. These are the only terms that will survive, okay. So long as n is not 0 or 1, each of those terms is going to go to 0, alright. So you get only a contribution if you take the limit as imaginary part of tau tends to plus infinity, you are going to get only 2 terms, 2 finite non-zero terms. And what will you get? You see, we will get limit imaginary part of tau tends to plus infinity of E3 tau minus E2 tau by e power I pi tau. What you will get is, see, if I put n equal to 0, okay, I will this will become 1, okay, and then I will get e power I pi tau, and e power I pi tau is going to go to 0 as imaginary part of tau goes to infinity. So essentially I am going to get 1, and similarly for this also, when I put n equal to 0 I will get 1. So I will get 2 into 4 pi squared, which is 8 pi squared, alright. And then when I put n equal to 1, the reverse is going to happen. When I put n equal to 1, you see this will become e power I pi tau, this will also become e power I pi tau, that is going to go to 0, and this is going to become when I put n equal to 1, this is going to become 1. So again I will get a 1 here, I will get a 1 here, I will get another 8 pi squared, so I will get 8 pi squared plus 8 pi squared, so I will get 16 pi squared, okay. Now combine this with the fact that as imaginary part of tau goes to plus infinity, E1 tau minus E2 tau goes to pi squared, because here this will go, the only contribution you will get, as I told you, was from the term n equal to 0, and in that case you will get a pi squared, alright. So this will tell you that the limit as imaginary part of tau tends to plus infinity of lambda of tau by e power I pi tau is 16, okay. So that is how you get that estimate, okay. So this estimate is very important, right. Now having done that, I will try to go and trace the image of this there, okay. So that again involves a couple of simplifications.